Hello everybody, I am Rocky Talchabhadel, currently working as a postdoc researcher in Disaster Prevention Research Institute, Kyoto University, Japan. The topic of my presentation is evaluating the impact of land use land cover change on soil loss and sediment delivery ratio across the West Rapti River basin, Nepal. Here is a list of co-authors uh, involved in this study. These are the content of my presentation. I would be mostly talking on soil loss and sediment delivery ratio. Soil erosion is an ongoing geomorphic process which is affected by multiple factors such as soil, topography, rainfall, land use, and under climate change and land use change, these factors are anticipated to alter and affect the soil erosion. Revised universal soil loss equation is one of the popular approaches to estimate soil erosion. In revised universal soil loss equation, climate change effect can be seen in R factor and land use change effect can be seen in C factor and P factor. We have carried out climate change impact assessment on the selected study area. You can find a detail on the paper mentioned here. In that piece of work, we developed a daily rainfall based R factor estimation and check with sub-hourly rainfall based R factor and use the daily rainfall based R factor estimation model to see the climate change impact assessment. We use 6 climate model data of daily temporal resolution under 2 warming scenario. So the good thing is we try to make a model where daily rainfall can be fed to estimate R factor. By doing, we try to quantify the climate change impact assessment on the study area, and we found almost about 10% increment could happen in the selected study area under climate change. With the continuation of that research, now we are focusing on land use change impact assessment. And before going to the study area, I would like to talk a bit about Nepal. Maybe some of you might not know where exactly Nepal is. Nepal is a landlocked country surrounded by China at north and remaining side by India. The latitudinal distance of the country is very small, but even in small latitudinal distance, the elevation ranges from almost 0 meter to 8,848 meter, the highest peak of the world. So from south to north, the climate varies from almost tropical to polar. The diverse in physiographical and climate makes this zone having lots of water-induced disaster, including soil erosion. And particularly the study area, which is located in southwest, southern belt of midwestern Nepal. The elevation ranges from almost 100 meter to 3,500 meter. Figure A shows land use land cover data. B shows dominant soil types of the study area. Some of the remarkable thing of the study area that I mentioned here is Almost 60% of land is covered by forest and almost 33% by agricultural land. Elevation ranges from 100 to 3600 meter. As I already mentioned, even the area is small, it has diverse climate. In this study area, the climate varies from temperate at upper region to tropical at lower region. And most importantly, precipitation varies a lot during intra-annual. For instance, July alone contributes almost 30% of annual precipitation, and during monsoon period that starts from almost mid-June to September, almost 80% of rainfall happen in just 100 to 120 days. So the erosion problem is serious because of localized phenomena of precipitation, the diverse topography, and also the change in or the scenario of land use land cover. Why we select this study area? One of the main reasons is the better availability of denser network meteorological station. We try to select the study area where it has lots of meteorological station and hydrological station, so that the meteorology that we develop can be validated with suspended sediment data of river, and the denser network of meteorological station can be used to replicate the real scenario of varying climate. Another important thing of this study area is the study area originates from the middle mountain of country and enters the lowland, meaning this is the typical catchment of Nepal where soil erosion is common, where the rivers are non-snow fed and they have a quick response time upon extreme precipitation due to the steep topography. So heavy rainfall, soil erosion and flooding are common problems in such catchment, including West Rapti River basin. Finally, our plan is to apply the methodology that we develop here in any other basin which have less number of meteorological stations or even ungauge meteorological station adjacent to the selected watershed. Talking about soil loss and sediment delivery ratio, in this research we use INVEST model, which is integrated valuation of ecosystem service and trade-off, and the sediment delivery ratio of INVEST model needs soil loss estimation, and for the estimation of soil loss, revised universal soil loss equation is used. The input data for the model INVEST is R factor in raster format, soil erodibility factor in raster format, land use in raster format, then a table that complies the land use type for C factor and P factor, and ultimately a elevation raster, that is DEM, digital elevation model. From the digital elevation model, the LS factor is calculated by the model. In previous study, we have already developed R factor based on daily data, which was also checked with sub-hourly data. So we use same R factor raster data. And for K factor also, we already developed data for the study area. In previous work, we made all other things constant except R factor, so that the quantification of climate change was done by changing R factor. But now we are changing land use and looking after the land use change impact on soil loss. So we did not change R factor at this moment because if we change both R factor and land use factor at the same time, it would be difficult to quantify the land use change impact on soil loss. And another step in future, we will combine the combined effect of climate change and land use change to get a real knowledge of what might happen in future. But for this moment, this study will focus on the only land use land cover change. And in invest model for sediment delivery ratio, from the elevation data that we give as a DEM, the LS factor is calculated using Desmet and Gower method. And M is again the RUSLE length exponent factor. With this governing equation, the soil loss can be estimated. The most important thing that I want to share in this presentation is related to sediment delivery ratio, because after the estimation of soil loss in the catchment, we need to understand how much the produced sediment can be eroded or can be transported to the stream, because all the sediment produced from the catchment cannot be transported to a stream. Some of the sediment may retain on the way. So the spatial distribution of that information is more crucial. To focus on that thing, this invest model calculates firstly connectivity index, which is mainly dependent on upslope area transport and downslope path retention. So with this information, sediment delivery ratio is firstly computed in the model, and from the information of soil loss and sediment delivery ratio, the model estimates how much sediment will be eroded and how much sediment will be deposited that doesn't reach the stream. And another part of the research here I would like to focus is land use land cover. For generating future land use land cover, we use, at this moment we use 6 variables: aspect, slope, altitude, distance from city, distance from river, and distance from road as a variable to generate a land change modeler. We use test model. From the available data of 3 decades, 1990, 2000, and 2010, we develop a land change phenomena which were governed by the selected variables. This is not the final model. We are working to add more variables so that the land change can be replicated in more precise way. This figure shows the change in land use type from 1990 to 2010, where it is clearly seen agricultural land is increased and it is compensated by decrease in forest. With the change that has been detected with previous data, we forecast for the future up to 2100, and our target is to validate the 2020 anticipated land use land cover data with the present data of Google Earth and Landsat images, which is currently ongoing. So the model right now for land change modeler is not the final one. We are working on it, but I would like to show some of the results from the preliminary analysis. Here in this map, the black color shows connectivity index calculated This is for 2010 case, and the red color is for upslope area transport, and the yellow color is for downslope path retention. From this information, a sediment delivery ratio can be calculated throughout the catchment. And from the revised universal soil loss equation, potential soil loss can be estimated. With the combination of this soil loss and sediment delivery ratio, a spatial distribution of sediment deposition can be finalized, from where we could know the produced sediment, how much has been deposited and how much is on the way, and how much is eroded in the catchment. So this type of spatial distribution of eroded and deposited sediment is very crucial for effective sediment management. This is a soil loss for 1990. In 2010, after 20 years, you could see a visible increment of soil loss because of increment of agricultural land. And with the information from land change modeler, this is a particular representative example for 2030. If you see in the case of 2010 and 2030, there is a significant anticipated changes in soil loss. As I already mentioned, the land change modeler is not the final one, so we are working on it, but we could get a tentative idea that under changing land use, the study area will have increased soil loss. And these are the discussions and outlook that I want to share with you. We applied the in-base sediment delivery ratio model to map overland sediment generation and delivery to the stream. A shift of land use land cover showed significant alteration of amount of sediment detaching and running off the watershed. During the 3 decades data, we found decrease in forest area was compensated by increase in agricultural land, and a small rate of soil loss was produced from forest land, and in contrast, a significant use rate of soil loss was produced from agricultural land. Therefore, the projected increment of agricultural land in future periods showed accelerating soil loss under changing land use land cover. Most importantly, the combination of soil loss information and sediment delivery ratio provides information on sediment export, how much sediment will be eroded from the catchment, and the sediment retention, meaning how much sediment is retained which doesn't reach the stream. So this type of combination of universal soil loss equation and sediment delivery ratio is necessary for effective management of sediment across the catchment. Thank you. This is what I want to share. Even I tried to make some results, some analysis are still undergoing. If you have any question, you can send me email. I am happy to get your comments.